Hi, this is Physics 1020 and 1090. This is the lecture for Wednesday, April 8th. We're in Chapter 29 on nuclear physics, and this is the second video for Wednesday. We're going to be talking about radioactivity, and in particular, nuclear decay and half-life. So first, a little bit about radioactivity and how it was discovered. Radioactivity was discovered by a French physicist, Henri Becquerel, in 1896. He was interested in studying fluorescence. Fluorescence means light comes down, hits a substance, and that substance gives off something. It could be particles, it could be other light, it could be X-rays, which you can record on a piece of film. So his hypothesis is light came down and caused this uranium-containing material to give off some signal that would be developed by the film. And I'm going to read to you a little bit from The Making of the Atomic Bomb, the famous story on how he did this experiment. It worked, but then there wasn't much sun in Paris for a few days, so he stuck this experiment in a drawer, and it still worked without the light. So let me tell you that story from The Making of the Atomic Bomb. And we have the Frenchman, Henri Becquerel, was an expert on phosphorescence and fluorescence, in his case, particularly of uranium. He heard a report of Röntgen's work at the weekly meeting of the Académie des Sciences on January 20th, 1896. He learned that the X-rays emerged from the fluorescent glass in Röntgen's experiment, which immediately suggested to him that he should test various fluorescing materials to see if they also emitted X-rays. He worked for 10 days without success, read an article on X-rays on January 30th that encouraged him to keep working, and decided to try uranium salt, uranyl potassium sulfate. His first experiment succeeded. He found that the uranium salt emitted radiation, but misled him. He had sealed a photographic plate in black paper, sprinkled a layer of uranium salt onto the paper, and exposed the whole thing to the sun for several hours. When he developed the photographic plate, I saw the silhouette of the phosphorescent substance in black on the negative. He mistakenly thought sunlight activated the effect, much as cathode rays released Röntgen's X-rays from the glass. The story of Becquerel's subsequent serendipity is famous. When he tried to repeat the experiment on February 26th and again on February 27th, Paris was gray. He put the covered photographic plate away in a dark drawer, uranium salt in place. On March 1, he decided to go ahead and develop the plate, expecting to find the images very feeble. On the contrary, the silhouettes appeared with great intensity. I thought at once that the action might be able to go on in the dark. What was going on? Energetic, penetrating radiation from inert matter, unstimulated by rays or light. So, that's the story of Becquerel and the discovery of radioactivity. Now let's talk a little bit about the mathematics of radioactivity. When substances decay radioactively, they generally fall off according to an exponential function like shown here, and they fall off with a certain half-life. So, suppose at time 0, you have 256 atoms. At time t1/2, which will take us our half-life, so after one half-life, you now have 128 atoms. After 2 half-lives, you have 64, half of 128. After 3 half-lives, you have 32, half of 64, and so on. If you wait 8 half-lives, you're down to 1. Started with 256, down to 1. So you can see that you start with a large number, and then it decays away in this exponential fashion, getting closer and closer to 0, never quite reaching there. So that's the characteristic function of how substances behave when they have a falling with a half-life. Let's describe it a little more mathematically. The exponential function that governs this is the number at time t is equal to the original number, n0, times e to the minus lambda t. Okay, what's e? E is probably the most famous a non-integer other than pi. That's 2.718 ... That is the base of the natural logarithms. It is what we often use to take powers of when we are dealing with exponential decay. And lambda is what's called the decay constant. It determines how fast the decay is going to happen. So there ought to be a relationship between lambda and the half-life. So let's see if we can find it. We're going to take our original equation and we're going to say what time does their amount decay to half the original amount. So for t, we'll put in t1 half. And for the number, we'll put in the original number, n0, divided by 2. So now you see you have n0 over 2 equals n0 e to the minus lambda t1 half. Now you can cancel out the n0s and you get 1 half is e to the minus lambda t1 half. Next step is to take the natural logarithm of both sides. So the natural logarithm is the inverse of the exponential function. So you take the natural logarithm of this left side, you get log of 1 half. And you take the natural logarithm of the exponential, those two cancel, and you just get the minus lambda t1 half there. The logarithm of 1 half is minus 0.693, but that minus sign will cancel that minus sign. And you end up getting 0.693 is equal to lambda t1 half. Or in other words, the half-life is 0.693 over the decay constant. So there's a simple relationship between half-life and decay constant. Now let me warn you a couple things. First of all, you're going to need to understand logarithms, which, like I said, is the inverse of the exponential function. Second of all, there's two types of logarithms in the world. So here's my calculator. We're going to use this logarithm, the natural logarithm, logarithm base e. There's also logarithm base 10. You see, if you look closely, logarithm base e is the opposite of e to the x. Logarithm base 10 is the opposite of 10 to the x. So you make sure you know how your calculator works and which key is the natural logarithm and which key is the logarithm base 10, and don't get them mixed up. Let's look at an example. Here we're going to look at the decay of iodine 131, which has a half-life of 8 days. Iodine 131 is actually used in medicine. The thyroid gland takes up iodine preferentially. So if you put in iodine 131, it will get taken up by the thyroid and it'll sit there and decay. So if a person has thyroid cancer, they're often given iodine 131, and it will selectively go and irradiate the cancer and kill the cancer cells. So how long until iodine 131 decays to 5% of its original amount? So let's see if we can see how to do that. Okay, first thing we're going to do is we need the decay constant. We have the half-life. So the decay constant is 0.693 divided by 8 days, the half-life, or 0.0866 inverse days. The units of the decay constant is always 1 over some time unit. So we'll put it into our exponential equation. We want to know how long until it's 5% of its original value. So 0.05, that's 5% of the original value, n0, is equal to n0 e to the minus lambda, which is 0.0866 times t, time. That's what we're trying to find, how long. So again, n0s cancel. We will take the natural log of both sides. So we get the natural log of 0.05 equals minus 0.0866 t. So let's see, natural log of 0.05. I'll take 0.05 and I'll take my natural log and I'll get a negative number. It's about minus 3 there. So the minus 3, the minus sign will cancel this minus sign. So you basically get a third of this. And then you can solve for time. So you'll get solve for t. And what you'll end up getting is time is equal to 34.6 days. So that's how long it's going to take for the I-131 to decay. Now, if you ever kind of want to check your work because you're not quite sure you're doing your math right, you can always make a little table. Say you start with 100 isotopes, 100 atoms of iodine at time 0. Well, then after one half-life, which is 8 days, you should have 50. After 16 days, you have 25. After 24 days, 3 half-lives, you're down to 12.5. After 32 or 4 half-lives, you're down to 6.25. After 40, which is 5 half-lives, you're down to 3.13. But we wanted to know when it was 5%. So that would be down to 5 because we started with 100. It should be somewhere between 32 and 40. So you'd expect it to be about somewhere 35-ish. And sure enough, we got 34.6. So it's kind of a way to check your work if you're ever just not quite certain you're doing it properly. Now, radioactivity happens over vastly different timescales. Different isotopes can have way different half-lives. For instance, uranium-235 has a half-life of 0.7 times 10 to the 9th years, so 0.7 billion years, or 700 million years. That's a long time. It's a significant fraction of the age of the Earth. However, we talked about oxygen isotopes in a previous video. We talked how oxygen 16, oxygen 17, and oxygen 18 were all stable. How about oxygen 15? Well, oxygen 15 is not a stable isotope. It decays, and its half-life is 2 minutes. So 2 minutes compared to billions of years, that's a vast difference. And if you go down to oxygen 13, its half-life is only 8 milliseconds. So I guess what point I want to make is that you can get way different half-lives depending on the isotope you're dealing with. Here's a question that I want you to do. What fraction of the uranium-235 that formed with the Earth is present in the Earth today? Okay, so here's what you need. You need to know, first of all, the half-life of uranium-235. I told you that in the last slide here. 0.7 times 10 to the 9th years. And you need to know how old the Earth is today. So the age of the Earth now is 4.5 times 10 to the 9 years. So the question then is, what fraction of the uranium-235 that formed with the Earth is present in the Earth today? I want you to stop this video and do that calculation, and then we'll go over it. All right. Well, first thing we need is our decay constant, which is 0.693 over the half-life. The half-life was 0.7 times 10 to the 9th. 0.7 is almost the same as 0.693. To at least to a good approximation, that's just 1 times 10 to the minus 9 for the decay constants. 10 to the minus 9 inverse years. So now we'll put it into our equation. N is equal to N0 e to the minus lambda t. We're asked for the fraction that remains of the original. So the fraction we divide through by N0, the original amount, and this would give us the fraction of the original amount, is just e to the minus lambda t. E to the minus 10 to the minus 9 times 4.5 times 10 to the 9, the age of the Earth. Well, 10 to the minus 9 in the lambda will cancel 10 to the 9 in the age of the Earth. You just get e to the minus 4.5. So I'll take my calculator. I'll put in 4.5 negative, and then in my calculator, to get the exponential function, I do a second and then press that key, and I would get 0.011. So I get that the fraction left over is 0.011, or about 1%. So there's certainly some uranium-235 formed when the Earth formed, and there's only 1% of it's left now. That may seem like a small amount, but there's a lot of uranium-235. Avogadro's number, or much more. So there's still some uranium-235 in the Earth now, but it's rather rare. Next, I want to talk about an example of carbon dating. Now, carbon dating is not when two carbon isotopes get together and go to the movies. Carbon dating is a way to try to determine how old some organic object is. So the half-life of carbon-14 is, sometimes we write carbon with C with a superscript 14. Sometimes we write the name of the element out, -14. They mean the same thing. The element carbon, isotope of carbon, which is 14, has a half-life of 5,730 years. So we can calculate its decay constant. Now, why is there any carbon-14 around? Well, carbon-14 is constantly being produced on Earth. How is that? Well, these cosmic rays come in from the sun, these highly energetic particles from the sun, and in the atmosphere, which is 80% nitrogen, they'll hit a nitrogen atom. And it'll cause a nuclear reaction, and we'll talk about nuclear reactions more in future lectures. It'll cause a nuclear reaction which will create carbon-14. So you get carbon-14, which usually then takes on a couple oxygen. You have carbon dioxide, which contains carbon-14 in the atmosphere. It's constantly being produced, but it's also constantly decaying. So it reaches an equilibrium where in the atmosphere you have a ratio of carbon-14 to carbon-12, the stable form of carbon. And that ratio is very small, 1.3 times 10 to the minus 12. So there's not much, but it is measurable, and you get a constant amount of carbon-14 in the atmosphere. Okay, now, plants take in carbon dioxide and use the carbon dioxide to create all their biological molecules. So as long as plants are alive, they have the same carbon dioxide, carbon-14, carbon-12 ratio as does the atmosphere. And animals eat plants, so animals also have the same ratio, carbon-14 to carbon-12. Once a plant dies, it's no longer taking in carbon dioxide from the atmosphere. Then it just sits there and the carbon-14 decays away. So the carbon-14 will eventually decay, but carbon-12 is stable. So the ratio 14 to 12 is going to decay away. It's going to initially, just when the object dies, its value is going to be 1.3 times 10 to the minus 12, the atmosphere ratio. But then it's going to decay away exponentially with the same rate constant as decay constant as carbon-14 has, because carbon-12 is stable. So here's the equation which can allow you, if you know what the carbon-14, carbon-12 ratio is now, to figure out how long ago that plant died. So here's the problem I want you to solve. An ancient wooden axe handle at an archaeological site has a carbon-14, carbon-12 ratio of 0.45 times 10 to the minus 12. It's a dimensionless number, it's a ratio. How old is the axe handle? So what I want you to do is stop the video, do the calculation, and then we'll compare our results. Here we go. All right, so your carbon-14, carbon-12 ratio. Initially, it was the same as the atmosphere, 1.3 times 10 to the minus 12, and then it decayed away, e to the minus lambda t. We can get the lambda, 0.693 over the half-life. And now we have what we measure the carbon-14 to carbon-12 ratio to be is 0.45 times 10 to the minus 12. So 0.45 times 10 to the minus 12 is equal to 1.3 times 10 to the minus 12, e to the minus lambda t. T is what we're after. So these both, you divide through by 1.3 times 10 to the minus 12. Well, the 10 to the minus 12s will cancel. You get 0.45 over 1.3 is equal to e to the minus lambda t. 0.45 over 1.3 is 0.346. Here you found your lambda, so e to the minus 0.00012 t. We're going to take the log, natural log of both sides. That will cancel out the exponential. You get log of 0.346 is equal to minus 0.00012 t. Solve for t. Okay, well, if you do that calculation, what you'll find is you get 8,844 years to be the time since the axe handle was a living plant. So it gives you the age of that archaeological object. Now, a few things to say about carbon-14 dating. First of all, it is an extremely common and important in archaeology trying to date objects, especially of human origin. You know, we can use just historic history to date a lot of objects that are, say, 1,000 or 2,000 years old, or maybe even 4,000. But before that, the only way we have to determine the age of an object is through this radioactive dating. Now, you can't do this back too long ago. It was about 5,000 years was the half-life. If you tried to go back, say, 100,000 years, that would be 20 half-lives. The amount of carbon-14 would have decayed to such a small amount that it would be immeasurable, and the whole problem wouldn't work. So you can only use this for a few tens of thousands of years old. There are other ways to measure older rocks and other objects, but carbon-14 dating is useful for measuring objects that are 10,000, 20,000 years old, which is great for early human history, prehistory, before historical record, but not too long ago. Another thing is you need these carbon-14, carbon-12 ratio. And how do you get that? Well, if you remember back to when we talked about a mass spectrometer, that's exactly the type of device you need in order to measure the amount of different isotopes. They have different masses, so they form paths in the magnetic field by different amounts, and that's what you can use to get those ratios. So that is the way you'd solve the carbon-14 dating problem. Again, another classic example of using radioactive decay. Let me show you one more example here. Here you have a case where you have not just a simple isotope decaying away, you have a decay chain. So you start with isotope A, which has a real long half-life. Think something like uranium-235. And it decays to isotope B, which itself is not stable. And in a very short half-life, it will decay to isotope C, which is then stable. So you have this intermediate step. So sometimes you can get these chains developing. So let's say you started somehow with pure isotope A. Maybe you just somehow separated out all the uranium-235, so it was pure uranium-235, and you wanted to see what happens. Well, the amount of A would then decay away exponentially, just like shown here, just like we talked about before. Now, originally you didn't have any B, but as A decays to B, B will build up. But then eventually B will reach a maximum and begin to decay away because your A will decay away. So there's not much producing B, and B will therefore decay away also. And there'll be a lot less B than A present, especially if B is real short half-life compared to A. So you end up getting a situation where B is a lot less than A. You just have a little bit of B present, even though there's a lot of A present, because the B will almost immediately then decay away to C. C will just build up until all of it becomes C at a long time. So it's interesting that you can have this kind of decay chain where you have a lot of A present, even though it's decaying away, but just a little bit of B. However, usually you're not detecting how much of B is present. Usually what you're detecting is the decay rate. You have a Geiger counter or something that's measuring when these decays happen. And what you find out is that the decay rate is the same for A and B. That is, both of them will contribute equally to the decay, even though there's hardly any B present, because B has a much shorter half-life, so a much higher rate of decay. So every time an A decays to a B, the B will then almost immediately decay to C, so you see one decay from A, one decay from B. So even though there's not much B present, it has a decay rate that's the same as A. So we're going to see in the future lecture, we're going to see the case of uranium will cause a long decay chain for A, B, C, D, E, F, and each one of those will be decaying away, and they'll all have about the same decay rate, even though they're all very slow concentrations in these rocks. We're not going to do these case mathematically, but I wanted you to see what happens when you have a short half-life. Finally, decay rate. Well, decay rate is usually measured in decays per second, or 1 becquerel after the discovery of radioactivity. So just like 1 hertz is 1 oscillation per second, 1 becquerel is 1 decay per second. And that's an awfully small unit. If you have a large sample, you're getting a whole lot of decays every second. So sometimes people measure it in units of curies. 1 curie is 3.7 times 10 to the 10th decays per second. So curie is a much larger unit than a becquerel. All right, so that is the story of half-lives and a little bit about radioactivity. But the question now is, what are these decays actually decaying from and decaying into? What's the nature of radioactive decay? In our next lecture, we're going to talk about the different types of radioactive decay.